When people from places like Arabia, China, and India tried using ASCII, they hit a major problem. Their entire language were missing. So what happened next? What was invented to fix this global communication gap? Stick around because the answer changed the digital world forever. Unicode is a complex topic to digest. It took me several days to understand what's going on in Unicode. You're not alone to feel intimidated by its complexity. In this video, I will use real-life examples to explain Unicode so everyone, even you, can understand it. Remember in our previous videos, I said that ASCII didn't have enough numbers to support all languages. And also I said that ASCII was upgraded to Extended ASCII to support more characters, which was still not enough. I said that Unicode was invented to solve that problem. Unicode can represent any character you can think of. Doesn't matter the platform, device, language, or even the operating system. I also mentioned that it's backward compatible with ASCII, which means that it uses the same 128 values for the characters represented in ASCII. What about the additional 128 characters? As I said in my previous video about extended ASCII, different vendors made their own extended ASCII. So I do not know which extended ASCII variant Unicode decided to use. But I know for sure that it made one universal encoding code for everyone to use. Want to know another cool thing about Unicode? It supports emojis. How cool is that? Remember in ASCII, I used to use the word character for each symbol and letters. But in Unicode, I don't. And instead, I use the word grapheme. But why? Because you see, I call this letter a character, and you call it too, right? I also call this character a character, but this is not a character. It's made up of two characters, the letter E and the accent. I mean, I can call it two characters, but that wouldn't sound ideal calling this two characters, while in our brain we see it as one. That's why they decided to use the word grapheme to describe what we see on the screen, even though it's made up of different parts. Think of it like a Lego. The one character is one piece of Lego, and a grapheme is the final build that you get by putting the small pieces together. So these are characters or Lego pieces, and these ones built from combining them together. Now, after putting the Lego pieces together, we get the final model. We get this accent letter by putting E and the accent, and this woman emoji by putting this emoji with this skin color. The same scenario exists in Unicode between a character and a grapheme. Hope that made sense. How does Unicode represent emojis or Asian language letters? It uses different numbers of bytes to represent one letter. For example, we need 4 bytes to represent one emoji, 3 bytes to represent a letter in an Asian language, and 2 or 1 bytes to represent other things. Let me explain this again with a real-life example. Let's say you have a shipping company. Every item someone sends needs to go into a box. Now, ASCII letters needs 1 box or 1 byte because they're tiny. Now, emojis are like giant stuffed toys that you can't fit in an ASCII box. You need a box that's 4 times bigger than an ASCII box, which means 4 bytes. Sending a thumbs up emoji in a text message is like shipping a giant teddy bear. Cool, expressive, but needs a huge box. Now for Asian language like Chinese, Japanese, or Korean, think of them like a beautiful ceramic bowl. They're smaller than emojis, but bigger than ASCII box. They would fit in a medium-sized box, that would be 3 bytes. Hope that made sense. I will explain how Unicode actually stores them later in this video. Unicode comes with its own numbering system, unlike ASCII, and that's hexadecimal. It uses hexadecimal to represent the binary value of a grapheme. It represents it like this: U plus 0041, which is called code point, which is the value for the letter A. If you convert 41 to decimal, you will get 65, which is the decimal value of A in ASCII. Now, why do we use hexadecimal? Because it would take so much effort to handle each binary number for every single emoji or language letter. Go watch my video about hexadecimal. I have gone through the hexadecimal in that video. Let's see how Unicode represents different graphemes. Every code point starts with the letter U, which means Unicode, followed by a plus sign, and 4 or 5 numbers which are in hexadecimal. The Unicode Consortium, about the people who manages the Unicode, uses a procedure to determine what value can be given to an emoji or a language letter. That's something beyond the scope of this video. Unicode uses UTF-8 to store the value of a grapheme, and there are other UTF versions as well, like UTF-16 and UTF-32, which we will not deal with them in this video. Let's draw a table of 8 bits. If a grapheme needs 1 byte, it will put a 0 here, which leaves us with 7 empty bits. Does that remind you of anything? It does. It reminds you of ASCII, because ASCII uses 7 bits. Remember the shipping analogy? It only needs 1 shipping box. If 2 bytes are needed, if we count from left to right, the first byte starts with 110, and the second byte starts with 10. Different shipping box size. If 3 bytes are needed, the first byte starts with 1110, and the remaining byte starts with 10 again. Once again, if 4 bytes are needed, the first byte starts with 11110, and the remaining bytes start with 10 again. Do you see a pattern here? The number of ones in these tables tell us how many bytes were used for a particular grapheme. And if we see 10 somewhere, we can know that that's not the start of a grapheme because it doesn't start with 11 or 111 or 11110. Now, the reason behind this is I don't know. I don't know the reason behind it. I just know that it works this way. Now, the bits that are empty, we will use them to store the binary of a grapheme. So 4 bytes can store 21 bits, 3 bytes can store 15 bits, 2 bytes can store 11 bits, and 1 byte can store 7 bits. Let's say we have an emoji and its code point is U plus 1F44D. First, I convert the hexadecimal to binary, which gives me this. Then I see where in this long string of bits are the most ones packed in one spot. That would be here. From the far left side, we start counting until we pass the last one in the pack. That would be 17 bits. Now, which one of these tables can fit 17 bits in them? That's correct. The 4-byte table, as it can hold 21 bits. Then, starting from the last table, we start to input the binaries one by one. Wait, that's 3 bytes. Why did you say it needs 4 bytes? Did you set us up? No, bear with me. You see, we don't have any other group that can fit 17 bits, so we don't have a choice but to go with 4 bytes. What do we do when we run out of ones? We borrow some zeros to fill them. Ta-da! Problem solved. This would be how this emoji is represented. Let's do another example. Let's take this Chinese letter. Its code point is U plus 7231, and this is its binary. Which group do you think this will best fit? If you said 3 bytes, you're right, because there are 15 bits when we pass the last number in the ones pack. Then starting from the last table again, we start to input the binaries one by one. Again, here we borrow a 0 to fill the remaining spot. Once we did that, here comes the question. If I convert these back to hexadecimal, would they be the same as they were before? The answer is no, because we just got new value. Did that confuse you? The new value is just to store them in UTF-8. The real value is still the same value as they were before, which is U plus 1F44D and U plus 7231. The other question is, how does Unicode determine what value to assign an emoji? Again, I don't have an answer to that. To follow a set of procedure which is beyond the scope of this video. That was all about Unicode. I know it was hard to get. Trust me, it was hard for me too. But hopefully I got it and you will too. If you found this video helpful, don't forget to share it with friends and family so they can benefit from it too. See you next time.